We present PlenVDB, a memory-efficient VDB-based Radiance fields for fast training and rendering. The input of our method is a set of sparsely sampled images from different views. And after training, the scene is reconstructed in our model. Then fed with arbitrary novel views, the model can render the corresponding images, even on a mobile device within real time. NeRF utilizes a MLP to model the scene. Although the MLP resolves the issues of resolution and storage, the query to MLPs is time-consuming, compared with the fast memory access. The training time often reaches hours or even days, thus limiting its applications. To speed up, DVGO directly optimizes a dense grid to represent the scene. Since the dense grid supports super-fast voxel access, it is convenient to perform trilinear interpolation and accelerate training. However, due to the sparsity of the scene, the dense grid is inefficient for storage. So, is there a data structure that balances between storage and performance? We are glad to introduce our PlenVDB. For users, the VDB is an infinite dense grid. Input a 3D coordinate, it will output the corresponding value or together with 8 neighbor values within constant time on average. For developers, the VDB is a 4-layer B+ tree. When querying the voxel 1, the accessor will cache all visited nodes. As the tree depth is 4, the access is fast. And when the next query 2 is the neighbor voxel, the VDB will check the accessor bottom up, which often hits for the first check. Thus, the VDB is able to perform fast trilinear interpolation and ray marching. Generally, the VDB enjoys the best of the both sparse and dense volumes. For fast training, we designed 3 VDBs. Given a coordinate, we perform trilinear interpolation to query the value in the data VDB. Then calculated by volume rendering and loss function, the gradient will be backpropagated. We accumulate the gradient into the grad VDB. When the optimizer calls the step function, we utilize the intermediate opt VDB to update the data VDB. Finally, we only use data VDB for fast rendering. For an image, we allocate one CUDA block and perform ray marching twice for each ray. The first ray marching visits only the density to count the number of the points that make valid contributions to the pixel. In the second time, we read out the color features and use MLP mapping to generate the color. For better performance and storage, we merge the 2 VDBs to one that saves the indexes pointing to the active voxels stored in an additional buffer. Finally, without any special optimizations, our PlenVDB achieves NeRF comparable QLT within minutes. And the speed is close to the state-of-art works for training acceleration. Based on DVGO, our PlenVDB achieves 4 to 5x speed up with well-established rendering technology, and reduces the memory occupancy for about 8 times. Here we present some videos for rendering quality comparison.